All right. So today we're starting a totally different topic. It's a totally different section. Today we're starting alkenes, right? If you remember, and then from these alkenes, we're gonna do a little bit of I think I'm gonna do some nomenclature today before I jump in with those reactions. And I'm gonna send y'all videos with the reactions so you can be prepped for Wednesday when we come back. We're gonna start talking about that. But I'm gonna introduce the reactions to you. Some of them today. So we're going to do nomenclature, right? That's a fancy word for naming. And then we're going to do structure, alkenes, cis and trans. And then we're going to do reactions of alkenes. So I'm going to tell you straight up, don't procrastinate with this. When you get those videos with those reactions in them, you need to start making you need to make a flashcard for every single reaction. That's the only way it's going to click. And I'm going to try to teach it in such a way that I classify the reactions so that you'll be able to box them up, right? But you got to make some flashcards. That's the only way that you're going to really, unless you just have a photographic memory, that's really the only way that you're going to survive this section is by making these flashcards for it, because there's a bunch of reactions. It's a bunch of different types of reagents that you're going to use. And so you need to be able to recall that. And the way you do that is to make flashcards. Memorization is bad for some things, but when you're trying to remember like the name of a reaction or the reagents used to carry out a reaction, there's nothing wrong with memorizing that. And even the outcome of a reaction, right? The mechanism part you really can't memorize, but you got to know the principles behind doing mechanisms. What's a nucleophile? What's an electrophile? What's a source? What's a sink? What do I use, single arrows or double-headed arrows? Or all of that stuff we've already learned up to this point. So when we get to this point, now is application, right? So we're going to talk about a bunch of different reactions. But first, let me just start out with some nomenclature. And I'm going to give you a real basic alkene like this. And so when you're naming alkenes, right, your alkene is your high priority functional group. That takes precedent over everything. So the key to nomenclature is, that's a couple of things. Number one is, which end do I number from? Or where do I start numbering? Right? With the alkene, you always start at the alkene. Following? So wherever the alkene starts is 1, where it stops is the next atom, that's 2, right? If it's internal, and this is a terminal alkene, by the way, that means it's on the end of a chain. If I could spell today, I'll be doing good. So it's a terminal alkene. If it's at the end of a chain, you're always going to start like that, 1 and 2. So 1, 2, 3, 4, 5, 6. So that's 6 carbons in that chain. So the parent, I think I gave y'all some of this before a little earlier. The parent is going to be hex, right? Because it's this, the Greek prefix hex means 6. And then ene is going to be the suffix. And then where is the alkene? So it's between 1 and 2, but I'm going to give it the lowest number possible. So I'm going to say that it's 1 hexene. Let me take this hyphen out so you don't screw that up. That's still a suffix. Sometimes you'll see it written like this, right? You'll see hex -1 -ene. Same thing. The ene is the suffix. That's my suffix. That's my parent chain. And then this is the location. It's the location of my double bond. All right. If I have something more complicated with more substituents, let me do that right quick. I hate nomenclature, by the way. I'm just telling you, but we got to do it. I just want to introduce you to it. So you will at least know the difference in cis and trans, and you'll know like some rudiments about naming. We got a whole module on nomenclature that's coming up. So that's why I'm kind of hesitant about taking a lot of time up doing it now. All right, so where's the alkene located here?
Would it be 2?
Yeah, so it's that's the end that we're going to start counting from. You see the end that's closest to the alkene, that's what we're going to start counting from. So this is 1, 2, 3, 4, 5, and 6. All right. So now the alkene is in between. I'm sorry, screwed up. There should be 2 here. 3, 4, 5, 6, 7. Sorry about that. So the alkene is between 2 and 3. And we have a functional group, a substituent at 5, right? Anytime you have something that's attached to your longest chain, we call that a substituent. And it's a CH3, so we call that methyl group, right? So this is, and the substituents always precede the name, right? So we have HEP as my parent. So HEP is the parent, ene is the suffix, and then the methyl group is at carbon 5, so we're going to stick that out here. So it'll be 5-methyl. And let me hold up 1 second. Move this back, because I need to put the 1 in there. 5-methyl dash 1 dash heptene, right? The 1 again, that's the no, I'm sorry, not 1, 2 heptene, because it's between 2 and 3. Five-methyl 2 heptene. Again, I gave the 2 a number, or the number 2 is telling me the location of my alkene. It's between 2 and 3, but I always give it the lowest number. So that's why I called it 2 heptene, right? And the ene tells me what? We have talked about this before, but it was briefly. What does the ene mean?
It's a double bond.
There's a double bond present. Good. Who was that?
Kayla.
All right, thank you. The ene means that there's a double bond present. All right. So one of the other things about alkenes, we're not gonna be able to talk about everything because we got all these reactions that we need to cover. So I'd rather spend more time with you learning that. But one of the things that we have to talk about is Alkene Stereochemistry. When you hear that term, stereochemistry, all it literally means is the 3D orientation of a molecule, right? So when you talk about stereochemistry, you have a couple of, well, you got 2 conventions really. The first one is the cis-trans convention, right? And that's where you have a double bond like so. And if both groups are on the same side of the double bond, then we call it cis or same. And then if both groups on opposite sides, then we call it trans. All right. So let's go back to that example we just did and add that in as a layer of information. So it's here between 2 and 3. All right. So what would you say about the alkene here? Is it cis or is it trans? Right. If you look at the groups that are attached to it, you got a carbon here, and you got a carbon on this side. What do you think? Are they on the same side of the alkene or opposite sides?
Opposite.
Opposite, right? So in the name, we got to include that. I didn't include it up top because I was really more concerned about showing you the convention for numbering the alkene. But here, right, I want to call this, I always put the stereochemistry first. So trans, 5-methyl, 2-heptene. So the trans part tells me what the stereochemistry of the alkene is, right? You can only tell that if it's internal. If it's terminal, then it can't be cis or trans, right? So if it's an alkene like this, like the first one we started with, right? There's no cis or trans there. So terminal alkenes cannot be cis or trans. Only if it's internal, right? All right, any questions about that so far? So how would I draw the cis version of that? Right, let me show you, and then we can talk about it. And then we're gonna move on to something else. You see the difference? This methyl group now is on this side, and then this one is on this side. So both groups are now on the same side of the double bond. Yes or no?
Yes.
All right. So this now becomes, instead of trans 5-methyl 2-heptene, now this becomes cis.
Can you repeat why it's cis again?
Say that again.
How do we know that it's cis again? By looking at it.
The cis part is right here. It's the actual double bond. So this is the double bond here, right? And the groups attached to it, the carbons attached to it, are both on the same side. You following?
Yeah. What does the trans look like again?
So the trans would be like this, right? You see how the groups attached to the double bond on opposite sides?
Oh, okay, yeah, I got you.
If I put the hydrogens in, that'll help too. So that's a hydrogen there and a hydrogen there. All right, and then on the cis, you'll see that the hydrogens are on the same side, like here and here. Right? So this is cis and trans refers to like disubstituted alkenes. If it's tri-substituted, then you have to use what's called E and Z. And I'll talk about that later. I don't want to get into that now because it's going to take up basically the whole class period. So let's look at, let's see. Yeah, we talked about that. I guess I could introduce, let me introduce an E and Z example because that's part of the stereochemistry too. So for tri and tetra substituted, right, you use E or Z. Right, these letters are basically, they're shorthand for German words. E is Entgegen and Z is Zusammen, but Z is same side, and then E is opposite side. So this is for tri and tetra substituted. So if you have a tri-substituted alkene, let me show you, let me give you an example of that. And I'm gonna put an H here. Let that stay there. And then I'll put OH here. And let that stay CH3. All right. So for this alkene, we want to determine what the if we want to determine what the stereochemistry is, we have to apply what's called the CIP rules. Con, I'll write it out. It's con angle.
Dr. Russell, when did you say we had to use the CIP rule?
If it's tri-substituted or if it's tetra-substituted.
Okay.
All right. So you use these what's called a con-angle prelog rules, and that's just basically, I'm gonna show you what that means. It sounds complicated, but it's really not. Right. So what you do is on each side of the alkene, you compare the priorities of the groups. Right. And priority is based on atomic number. So for this side, for the right side, you have a carbon and a hydrogen, right? So for this side, carbon is high priority. All right, and let me go back down here. So you're going to use the atomic number to determine priority. All right, so the atomic number, all you need is the periodic table for that. And so for on the right side, carbon is high priority. On the left side, the atom that's attached to the double bond is an oxygen here, and then a carbon here. Sorry about that. Let me get this together, get my life together. So you got an oxygen here, and you got a carbon here. Oxygen has an atomic number of 16, and carbon 12, well, atomic mass, right? All right. So on this side, this is high priority, right? And so now what you look for after you assign priority are the two high priority groups on the same side of each other or opposite. And in this example, they're on the same side. So this would be considered a Z alkene, right? Because Z means same side. Zusammen means same side. Eingeigen, which is E, means opposite side.
Dr. Russell,
Yes.
you said once you do the like high priority thing, you said, what did you say after that?
So if the high priority groups are on the same side of the double bond, then it's Z. You see how on the right side, the high priority is on the top side, and on the left side, the OH, the O is also on the top side?
Yes.
Yeah, so if they're on the same side of the alkene, then it's Z.
And how did you determine it was high priority again?
Use the atomic mass. I put atomic number down here, but it's interchangeable. You can use the atomic number or the atomic mass. All right, so we took that same example, but we changed the stereochemistry and put the OH down here. Why are people calling them in class? All right, now we have the OH here, or the O here, because that's all we're concerned about, right? And when we compare that to carbon here, the O is high priority still, just in a different place. Then on this side, I think there's a hydrogen here. We got carbon here and a hydrogen here. So the carbon is high priority. Right? And so you see now, relative to the double bond itself, the high priority groups are opposite to one another. Can you see that?
Yeah.
So this
Yes.
would be an example of an E alkene.
And it's because they're on the opposite side, right?
The high priority groups are opposite to each other.
Oh.
Let me 1 second.
Dr. Russell,
Yes.
so what do you mean when you say that it's on the same side?
Okay, can you see the alkene, the double bond
Yes.
right here? Can you see that you have basically you have a top side and a bottom side?
Okay, so you meant top and bottom.
You see that?
Yes.
So on the top side, the high priority group is on the right carbon, because you got to think about this in terms of the right side and the left side. So on the right side, which is here, right? The high priority group is at the top. On the left side, the high priority group is at the bottom. You see that? Or on the bottom side, on the bottom face. And so that means that they're opposite. They're not on the same side. So that means we call it E.
Okay. Thank you.
When you said we use the atomic mass, is it like a certain like number or something that?
Yeah, it's based on the periodic table. So carbon is 12, oxygen is 16, nitrogen I think is 14, the chlorine is 35, bromine 79, so on and so forth. You can get that information from the periodic table. All right. Any other questions about that?
Nope.
All right. So I think that's enough nomenclature. Let's jump in and start talking about something that's vital. I hate nomenclature. It's like my least favorite thing to talk about, as you can probably tell by the deadpan sound of my voice. But we're going to talk about some reactions of alkenes. Right, but before we talk about any of the reactions and the names and all that stuff, I want to point out like a bunch of different little things to look for. All right. So first of all of these reactions are going to happen on an alkene. I'm just going to give a real generic example. Right, so this is my alkene. Sometimes you'll see it written like this. If it's more than one step or more than one transformation that has to happen or more than one set of reagents, sometimes you'll see it written like this, right? Where you have one and then, so this is like a sequence. You'll see it written like a sequence. Right? You know, I bought this real fancy stylus from Amazon. I was all excited. Tried it out this weekend, worked fine. Tried it this morning, nothing. I give up. I'm just gonna keep using my finger. All right, so this is a sequence. So step one, whatever you get from that, that's going to be the precursor or the reactant that step two operates on. Are you following? I'm gonna give you an example. And then whatever you get from step two, that's what the reagents in the third step are going to work on. Right. So let me give you an example of a real reaction of an alkene. So let's say I want to take boom, and then I'm going to do in step one HCl, and then in step two I'm going to do SCH3 minus, and actually no, I'll do OCH3. And then that's going to give me, I'm going to draw the product, but I'm going to show you. So that's my product. All right. But let's look at what happens. So on the first step, we're not worried about the mechanism or anything like that, because we're going to talk about this reaction in great detail. So with the addition of HCl, that's going to add H and Cl across that double bond. So the H is going to add to one side, the Cl is going to add to the other side. So that first reaction is going to give me this as a product. Hold up. Let me just move this whole thing, because I don't want this to be screwed up when I post these notes. Copy it. All right. So then the first reaction is going to give me this, where the chlorine ends up here. Right? Are y'all following? So the chlorine ends up on this carbon. I'm going to tell you why later, so don't panic about not knowing why it's there. And then what this means is that in the second reaction, you see what the OCH3 minus is? This is what is getting reacted on, not the alkene, right? First reaction converted the alkene into an alkyl halide. Now you're going to add in the OCH3 as a nucleophile, and then chlorine is going to be your leaving group, which we talked about at length already. And so that's how I'm going to get to this product right here. But you can see that it's a sequence. It's not just going back to the alkene and reacting that. No, what we did was we reacted the alkene. Once that got used up in the second step, whatever the product is from the first step, that's what the OCH3 is reacting with. So, and the reason I'm saying all this is because some of these reactions we're going to see, there'll be sequences where you make something from the first step, and then in the next step, whatever you made from the first step, that's what's reacting in the second step. It's not the original start material, right? And that's very important to understand, because otherwise you're going to be pulling your hair out trying to figure out how I got from point A to point B, and not understanding that in between A and B, that was an intermediate step or another, a precursor to B, right? So sometimes you'll see the reaction written like that, like a sequence. Where you got step one, step two, and that's got nothing to do with the mechanism, which can also be a stepwise mechanism, right? We talked about that. It's got nothing to do with the mechanism. Every reaction is separate. That's what that means. When you see 1, 2, and 3 like that, it means every step is a separate step in the overall reaction. Right? This is how you write out what's called a synthesis, where you go from starting material to product. So some of your reactions you're going to see written like that. And when you see that, don't panic. right? Just know that it's a sequence. So once I'm done with whatever the reaction of 1 is, whatever I get from that, that's what 2 is going to work on. Whenever I finish that, that's what 3 will work on. So it's good to have that in your mind when you're going through these reactions. All right. Any questions? I know that was a lot. But this is the most difficult part of the class. I'll say that. I won't sugarcoat it. This is the hardest part of the class. It's going to take the most amount of work, and it's going to take the most work on your end, practicing after class, on the weekends, whenever, if you really want to master it. Because a lot of this stuff you're going to see again in part 2. And this is the part where you don't want to slack and just say, oh, I'll just get somebody else's notes, or I'll just find an old test that somebody took a screenshot of. Because I promise you, if you're trying to go past here and past part 2, you're going to professional school, if you're going to medical school, if you're going to graduate school, wherever you're going, this is the stuff that you're going to have to take with you. And if you just try to slide through, I promise you, when the rubber meets the road, you're gonna know that you slacked. So don't slack. All right. So let me go ahead.
Did the Cl, like, when the OCH3 became the nucleophile, did the Cl like just become its own like little like leaving group type?
It's the leaving group. That's a substitution, right?
Okay, yeah. That's
Yeah, it's a substitution on a secondary carbon. So the chlorine is just a leaving group. Now I wasn't showing that to talk about the mechanism, but yeah, that the chlorine is actually the leaving group in that second reaction, which is a lot of times how synthesis works, right? You have a reaction and you're trying to make something, but you can't get to it in just one step. So you need multiple steps. All right. Let me give you some of these alkene reactions. And I'm gonna take the alkene, I'm just gonna put in a generic alkene here in the middle and do what's called a reaction wheel. Let's see. Let me zoom in on that. So if I have an alkene like this, right? I got a bunch of reactions I can do on this, right? I can, if I add HCl to it, I can convert it into an alkyl halide, where chlorine is on the more substituted carbon, right? So if I add Cl2 to it, I can convert it into an alkyl halide where you have a chlorine on both carbons, right? And the reason I'm showing both of these reactions is because they're related. In that, what did I just make as a product? I made an alkyl halide. Anybody remember that functional group? So when I'm talking about classifying reactions, that's what I mean. Oh, how can I make alkenes into alkyl halides? Well, I can add HCl to it, or I can just add a halogen to it and do a halogenation, right? Or I can do another reaction to it. If I want a different type of alkyl halide, I can add chlorine. Hold up. Get my hand right together. I can add chlorine and then do the reaction in water, and I can actually get what's called a halohydrin. It just depends on what I want. All right, so all those reactions are dealing with converting alkenes into alkyl halides. Are y'all following that? You see how classifying them helps me now to narrow down what my choices are, right? If I know that I'm making an alkyl halide, well, I only know 3 ways to do that at this point. There's multiple ways, but here we'll say that these are the 3 ways that we're gonna learn with the mechanisms. right? So that's a way to convert alkenes into alkyl halides. What if I wanted to convert the alkene into an alkane? Well, if I just add hydrogen and use a catalyst to do it, we're going to talk about all of that. So don't panic, right? That'll take the alkene down to an alkane. Right? There's not really a whole lot of ways to do that other than hydrogenation. Right? So, but that's another reaction. And then another big reaction that we're going to talk about is taking alkenes and turning them into alcohols, which is another functional group, right? So we're going to talk about 3 ways to do that. Right? We can do, I'm not gonna put the reagents in, I'm just gonna call it. I'll put the name of the reaction in. We can do oxymercuration. Right? Or we can do what's called hydroboration. Don't panic. You're gonna learn you'll know what all this stuff means by the time we get through this unit. And then follow that up with oxidation. That's one of those sequence reactions where you make, oxymercuration is 2 really, where you make something from the first step, and then whatever you make from the first step, the second step is going to convert it into something else, right? But when you do oxymercuration, I'm going to show you the difference. They both make alkenes into alcohols, but the difference is the location of your alcohol, right? If you notice, oxymercuration, the OH ends up on this carbon. But if you do hydroboration, the OH is going to end up on the other carbon, right? And there's good reason for that. What if you don't want the OH to be on the secondary carbon? What if you want it to be a primary alcohol? Then you need a method. You need a method to do that. All of these reactions are nothing more than tools in a toolbox. Once you know what you want to make, then you go through the toolbox to figure out what tools you have to make it. That's all you're doing, right? And then what if I want to put an OH on both carbons? Well, there's a way to do that too, right? And let me see if I can fit the name in here. It's called osmolation. And you're going to learn what that means. So you got all these different tools, right? And then there's even more reactions than that, but I'm just going to introduce with that. But we're going to talk about ways to convert alkenes into carbonyls, ways to convert them into cyclopropenes. There's a bunch of different reactions that we can do. But these are just some of the main ones that we're going to learn, right? So all these are what? On this right side, these are all alcohols, right? So that's a class of reactions. Converting alkenes into alcohols is a class of reactions. Converting them into alkyl halides, that's a class of reactions. Converting them into alkanes, that's a class, right? And by the same token, converting alkenes into carbonyls, that's a class of reactions. Converting them into epoxides, all of these different functional groups, all of those are different classes of reactions. And some of them are a class within a class. Like the alcohol formation, that's oxidizing because you add an oxygen. And so all this stuff we're going to learn, I'm not just going to dump it all on you, even though I just did. But we're going to walk through like a bunch of these reactions and talk about how they happen as well. Any questions about anything so far? I know it sounds like a lot, but I promise you, if you do your part and you put the work in, I promise you, it's not going to be as bad as it looks. But you got to put the work in. You can't glide through this section. No questions? Is everybody mortified now?
Dr. Russell,
Yes.
in the beginning you said we should make flashcards. What did you mean make flashcards of what exactly?
Of the reactions. When you
Okay.
when I send a video today, you're gonna see in that video, and you'll see. Let me give you an example. So let's say let me give you one of the sets of reagents here. Let's say you wanted to do, or we can just do the halohydrin. Do you see how this is written? Where you start with the alkene. These are my reagents, and this is my product. That's a flashcard. And then on the back of it, you can write the features of the reaction, right? You can even put the mechanism. If you know the mechanism, you can put that on the back side. But on the front side, you would put the title of the reaction, halohydrin formation, show the starting material, which is the alkene, show the reagents, which are used to transform the alkene into the halohydrin, and then the product, right? That's an example of what you would have on a flashcard. Starting
All right,
material,
thank you.
reagents, product, and then any key features about that reaction. Because there's a lot of these reactions, they have specific outcomes in the product, and you can identify what happened, what reagents you use based on the product. I'll give you an example right here. You see how with the halogenation up top, you see how the two chlorines are on opposite sides or trans to one another? Right here.
Yes.
That's common. For halogenation, the two halogens, when you add them to the alkene, they always end up trans. That's a key feature of that reaction, right? Do you see right here that the chlorine from this reaction right? So you took the alkene, added HCl to it, and then you got an alkyl halide. Do you see where the chlorine is? It's on this, it ends up on this carbon, the secondary carbon, and not the other carbon. That's a key feature for that reaction. There's a reason that it happens in that way, and not the chlorine being on the other side. So that's what I mean by on your flashcards, you're gonna have you'll have the reaction, but then you'll also have the details about it. And that'll help you to learn the reaction and not just memorize the reaction. All right, that's a great question. All right, any other questions about anything that we've done? I know it's a lot, but I'm gonna walk you through it. I ain't just gonna throw you in the ocean. I'm swimming too, so we're all swimming together. So don't panic.
And you're gonna send out videos on this?
Yeah, I didn't want to send them last night because I know some of y'all were taking the exam still. And so that's why I just decided to wait until today. But I'm getting ready. Once I finish and we log out, I'm going to post these notes to Blackboard. I'll post a lecture from today to YouTube, and I'm going to send you videos to watch. But the videos are actually already in the module. If you, let me show you. I think I got Blackboard open. Yeah, the videos are all right here. It's the stereochemistry video, the degrees of unsaturation, which we'll talk about later, and the reactions, the different reactions, all that stuff is right here. But I'm still going to send the links out. All right, any other questions about